Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. Today's topic will see the problem solving case studies on mathematical behavior of PDE of Module 2. Okay, so let's see the question. So calculate the impact of Reynolds number, skin friction coefficient, frictional velocity, and spacing of grid points by varying Mach number. Okay, so first of all, whatever the numbers we have, let's say Reynolds number, Mach number, so these are the non-dimensional coefficients. Fine. So by varying these non-dimensional coefficients, so how does they impact on the skin friction coefficient and frictional velocity, and how do we vary the spacing of the grid points? So this is very important. So this aspect has to be calculated, predefined to before computing any CFD simulation. Okay. So first let's see what is Reynolds number. So Reynolds number RE is nothing but so rho V L by mu. So if we take in terms of free stream, so rho infinity, V infinity, and mu infinity. Fine. So this Reynolds number rho V L by mu. So the numerator term is called the inertial force, and the denominator term is called the viscous force. So density, velocity, and reference length. So reference density, reference velocity, and reference length, and the dynamic viscosity. So these parameters can define the entire flow properties for a fluid flow, so which is happening from one place to other place. Fine. So this is what we have. Next we have Mach number, so MA, or you can take it as M, so which is V divided by A. So here what do we have? So basically V infinity is nothing but your free stream velocity. So here Mach number we can take in two ways. One is like it's this flow velocity or the speed of the object. Okay, so if we consider flow velocity, that will be speed of the medium divided by speed of sound in the medium, or let's say speed of the flow divided by speed of the sound in that medium, or we can say V infinity as the velocity of the body divided by speed of sound in that medium. Fine. So these two aspects we have. We have Reynolds number, we have Mach number. Fine. Next, so if we vary Reynolds number, what happens? Let's say if the Reynolds number is low, or let's say it is high. So what happens actually? If the Reynolds number is low, so it can happen in two ways. So one is like either we decrease the density of the flow. So for a given body, so either we decrease the density of the flow or decrease the velocity of the flow. Okay. So in this aspect, we can reduce the Reynolds number, where if we decrease the velocity of the flow, so what happens? It happens to be for low Mach numbers. So why? Because we have the V infinity term which is common in the Mach number. Fine. So basically for high Mach numbers, let's say if RE is high and M Mach number is high, so let us take this as a supersonic case. Fine. So we have a supersonic case. For the supersonic case, what happens? You have Mach number greater than 1, and you have the Reynolds number very greater than 1. So RE is also, let's say, greater than 1. Let us take. So it is not even greater than 1. Let's say it is 10 greater than 10 power 5, 10 power 6, like that. But here for convenience we are taking like greater than 1. So here if RE is very higher, so what happens actually? So what happens to the skin friction coefficient, and what happens to the frictional velocity, and the spacing, so between the grid points has to be mentioned. So we'll see the relation. So what are the things which is affected? First thing, we need to see what is the thickness of boundary layer. So basically, as we know, the boundary layer is a layer which is present immediate to the immediate or adjacent to the body or the, let's say, the plate or any kind of equipment. So where the velocity u is 0 at the wall, and here it becomes u is equal to 0.99 times of u infinity. So after this, that will be u infinity. So boundary layer is a very thin viscous layer which is present adjacent to the body. Now, so how to calculate the thickness of boundary layer? Actually, that is very important. So we have delta, which is nothing but boundary layer thickness. So delta x, which is equal to under root of x divided by re of x. Okay, so this is an approximation, not exact value, but it's an approximation. So we can say in this way. So where 5 times of x divided by root of rex. So when we know the Reynolds number, how do we know the Reynolds number? So let's say the density value rho is 1.2 kg per meter cube, and velocity reference, let's say velocity we can take it as u infinity, we can take it as 400 meter per second, we can take in this way. Next reference method, let us take it as 1 meter, and mu, let us take it as 10 power 5. Okay, so 10 power 5. So we have Newton per meter square divided by uh, meter per second by meter. So this, like, units you can take it. Fine. So which happens to be Newton second per meter square. Fine. So this is for the units per mu. Fine. So this mu value units I have calculated in this way, where tau is equal to mu into dou u by dou y. So the units for tau is Newton per meter square and mu, and here for velocity units meter per second divided by the dy units is meter. So from this we will be able to calculate what is the value of mu. So mu is equal to Newton per meter square into, so meter divided by meter per second. Fine. So this is what we have. So from this we got this. Fine. So now we know the values. So how do we calculate Reynolds number? So Re is equal to, so 1.2 into 400 into 1 divided by 10 power minus 5. So here what happens actually? So 12 force has to be, so 480 into 10 power 5. So which has to be like Re is equal to, so 4.8 into 10 power 7. So Reynolds number does not have any units. Okay, remember that actually. So Reynolds number does not have any units. So therefore it's a non-dimensional number. So which is the ratio of different forces. Numerator is the inertial force, denominator is the viscous force. So that's why force divided by force, there are no units. Okay, it's a non-dimensional number. Now, so we know the Reynolds number. So when we substitute this Reynolds number here, we will get the thickness of what? Boundary layer. Okay, so approximately, let's say if it has come something like 2 2 into 10 power some minus 4, or let's say minus 3 meter. So if we get, so I'm giving approximation, so then the thickness or the spacing between two grid points should be less than this. So this is one rough way of calculating the thickness. Now the other way is, now so we know the Reynolds number, so let us calculate the skin friction coefficient. Cf is equal to 0.026 divided by Re to the power of 1 by 7. So we have this formula to calculate the friction coefficient. So here you can see we need to calculate skin friction coefficient. So the formula of skin friction coefficient is 0.026 divided by RE to the power of 1 by 7. So we know RE is equal to 4.8 into 10 power 7. Okay, so we substitute here CF is equal to 0.026 divided by, so 4.8 into 10 power 7 to the power of 1 by 7. Okay, so therefore what happens actually, so approximately we will have some value, so which is of 0.012 something like that. So from this we will get the value of CF. Now here what is happening, so the Reynolds number is greater than what do you say, RE is greater than, let's say, 10 power minus 5. Fine. So here the Reynolds number, if it is increasing, so what happens, the skin friction coefficient is decreasing. So what is the meaning, at high Mach numbers and at high Reynolds numbers, so what happens, the skin friction coefficient is basically getting decreased. Okay, so this is one thing. Next, now the other thing is, when we decrease the Reynolds number, so you can see since it is in denominator, so what happens actually, so this have gonna increase. Fine. So this is the impact of the skin friction coefficient, based on the Reynolds number by varying Mach number. So here what is the Mach number that we get, M is equal to, so V is 400 we have taken, and A is something like 350. Okay, so M will be approximately 1 point something like 0.1 kind of, or let's say 0.5 kind of Mach number, like which is M is going to be greater than 1. Okay, so here we can see that the Mach number when it is greater than 1, so the skin friction coefficient CF is going to decrease. But to calculate, so tau of wall, shear stress of wall, which is rho u infinity square, or let's say u infinity square CF divided by 2. So this is the formulation for shear stress on the wall, or let's say the skin friction force, or let's say you can say that the frictional coefficient which happens, like which has come from the calculation of the Reynolds number, and which is applied here for calculation of tau of wall. Now the tau of wall, you can see that it is majorly depending upon the free stream velocity and the density and the CF. So here what is the meaning? As we increase the velocity, the coefficient may decrease, but the value of tau wall, the skin friction, like skin frictional force is increasing actually. Fine. So the coefficient may come down, but here as the velocity is doubled, or as the velocity increases, so the skin friction coefficient, the skin friction force is basically increasing by square times actually. Fine. So therefore tau of wall is equal to rho u infinity square CF divided by 2. So which happens to be increase in the value of tau, okay, by increasing u infinity, or increasing the rho. So CF value as it changes depends on the Reynolds number. Fine. So this is what we have. Next, u of frictional velocity is equal to tau of wall divided by rho. Okay, so once we calculate the tau of wall is nothing but the frictional velocity of the wall. Okay, sorry, this frictional force on the wall. So the frictional force from the wall, once we get, we will get what is the velocity of the flow for in terms of frictional quantity. So here this one we use it for spacing. Delta S is equal to y plus mu divided by u friction into rho. So this is what we have. Fine. So here what is happening? So the value of uf basically is showing a big impact of the spacing. So observe this term clearly. So here what happens? So basically this y plus. So y plus is nothing but it is a non-dimensional number. So which happens to be the uh, spacing between the grid points based on the profile. So this y plus value will vary inside the boundary layer based on their profile actually. So when you draw the boundary layer, let's say, so till here, so sublaminar layer or subviscous layer, you have one y plus value, let's say less than 5 or less than y plus value less than or equal to 5, and in between this you will have, let's say, y plus value greater than 5 and y plus value less than 150, some kind of thing. So these values, rough values, we can assume here. Once we get the approximate y plus value, and we know what is the value of mu, and so we will calculate what is the value of frictional velocity, and we know what is the tau of wall from the basic formulation which we had seen in the previous slide. So here we have, so here we have tau of wall. So in this tau of wall we will have the quantities of u infinity, cf and rho. So here we can see the uf value is playing a big impact here for the spacing. Now what is the meaning actually? So if the uf value increases, the frictional velocity increases, the spacing decreases. Or if the value of uf let's say it decreases, the spacing increases actually. So what is the meaning actually? Now, so how the uf value increases? So basically delta s increases when uf decreases, let's say. So this uf value, frictional velocity value, has a major impact for the spacing. So the other term y plus mu and rho, they are some standard quantities based on the flow regime or based on the boundary layer profile or based on the physics of the flow. So the y plus value will be chosen. Then mu value is obviously which is coming from the flow parameter. So if you take air, the mu value will not change. So density value will not change. But if there is a change, it will be very slight. But here the major factor which is uf. So uf is nothing but a frictional velocity is the major factor. So which is going to change the spacing. Fine. So how, like, if the uf value is higher, so higher in the sense what? How do we get higher uf? So if we have low density or if we have high frictional velocity or how high friction on the wall. Fine. So density parameter, like, it will not change that much. So if you have air which has density 1.2 meter, so that gonna change, let's say 1.2 to 1.1, most 1, or let's say at most 0.1, or let's say 0.5, 0.9. So in that way, very very low probable. Okay, so that is for on the body. Now that what happened for the density. If we see tau on wall, so tau on wall will increase when, so we saw, so we have seen here, so tau on wall increases when you have increase in u infinity velocity, when you have increase in density, when we have increase in cf. Okay, so this is what happens. Now here you can see the tau on wall increases when you have increase in free stream velocity, and when you have increase in what's it, density or cf. So majorly it depends upon the free stream velocity. The free stream velocity is basically increases, and this tau of wall increases. Then the UF value increases. Next, if the UF value increases, what happens? The spacing between two midpoints will decrease. So the delta S is nothing but the spacing. So when we are talking about Y plus, so we have a mesh, let's say. So this is the wall. So this is the grid point at wall. Let's say this is W1, this is W2, this is W3, this is P1, P2, this is P3. So distance between W1 and P1. So this distance is nothing but your delta S, let's say. Fine. And here also. Okay. You take any, let's say this is mesh line M1, this is mesh line M2. So spacing between mesh line M1 and M2 will not, let's say, will be same throughout the points, which, let's say, W1 P1, W2 P2, W2 W3 P3. So when you have a, let's say, flat plate, for a flat plate, so since there is no curvature and there are no some complex phenomena, the spacing between these 2 points, let's say W1 and P1, is same, and W2 and P2 is same, W3 and P3 is same. It will not change. Fine. So, but when you have curvature, what happens? Let's say you have a curving nature, something like this. So here, because of some concavity, or let's say convexity, so here this point, the spacing between those two changes. Here it is W3 dash, W2 dash, and W1 dash, let's say. So W1 dash, W2 dash, W3 dash. So you can see that the apparent changes will happen, and the delta S1. So delta S1 and delta S2 and delta S3, they are not equal actually. But previously, when we have the flat plate without any curvature, when it is straight, so the distance between line M1 and M2, so M1 represents basically its wall. So we take a flat plate or we take a curved plate, so that is a solid entity or a solid object, so which we say it as wall. So between the wall and the point particular P, so what happens? The distance is delta S. So we have delta S1, delta S2, delta S3. So delta S1 will be basically higher for let's say here, that's W1 dash, W2 it may be lower, and W3 it may be again higher. So delta S1, S2, S3, they are unequal when you have this curvature entity. They will be equal so when you have the flat plate at M1 actually, or the flat surface at M1. Fine. Now coming to the explanation of this one, delta S, which is depending on the y plus mu, uf and rho. So here the spacing between the W1 and P1, or W2 and P2, W3 and P3 is delta S will decrease, will what decrease when your UF increases. So at the end, what happens? Your frictional velocity is increasing when. So here we can actually give one conclusion where UF increases as tau of wall increases. Tau of wall increases. Next, how tau of wall increases? With respect to U infinity, it increases. Okay. So as the U infinity increases, so your Mach number increases and your Reynolds number increases. Fine. So this is what happens. Fine. But here only the CF value decreases. So for the simulation point of view, so what is happening? So as the value of UF is decreasing, the delta S increases. The spacing here, let's say this one may go to the new point here. So let's say this is P1 dash. So when your UF is high, or let's say sorry, UF is low. Now when UF is high, so this is what happens at the P1 double dash. Let's say this is the intermediate point where again it comes here. Fine. So this is what happens when the values of delta S, sorry, when the values of UF changes. Fine. So here we have seen clearly that the frictional velocity, or let's say UF value and tau of wall is basically uh, proportional, and they will increase based on the free stream velocity u infinity. So when the free stream velocity u infinity increases, ma increases, re increases. Now what is the reverse trend? So UF value decreases, tau of wall decreases, u infinity decreases. So in turn CF value increases, and from here what we have, M value decreases, M Mach number, RE value decreases, Reynolds number. So which is purely based on the free stream velocity. Fine. So this is the trend. What is like we have calculated the impact of the Reynolds number and the skin friction coefficient and the frictional velocity and the spacing. So here when it comes to spacing, so we need to add here. So delta S value, so what happens as UF value increases, since it is inversely proportional, this decreases. Okay, so here delta S increases. Fine. So delta S is nothing but the spacing between the grid points. So here the spacing between the grid points will basically decreases when UF value increases. Here the spacing between grid point will increase when UF value decreases. Fine. So there is one more parameter, let's say for the time parameter, which is called Courant number C, which is U delta T by delta X. Okay, this is for X Courant number, Cx. So Cy, let's say V, if you take U as the reference, U delta T by delta Y. Okay, so here the spacing is also important for the stability actually. Fine, it has an impact for the stability of a numerical scheme. So how it shows an impact? It shows a very big impact where the Courant number criteria is should be less than 0.5, or at most C value is less than 1. Okay, so this is the maximum, this is the maximum case, this is the maximum case, and this is the minimum requirement. Minimum in the sense, like let's say it can have C value 0.8, 0.9 also, but for most comfortably stability, so we have 0.5 actually. So if we have 0.5, then it will be like most likely be, and mostly it is stable. So if it is near in between that, sometime the Courant number may change when the spacing between the grid points changes. Fine. So here the spacing is showing an impact for the stability also. So therefore what happens actually, your Reynolds number, skin friction coefficient, frictional velocity, spacing, and these aspects are also showing an impact for the stability of the scheme. Fine. So here the C Courant number C is, let's say Kx, Cy, Cz. This is for 3D. Let's say you have the magnitude of Courant number. If you take, so this will be U delta T by delta X plus U delta T by delta Y plus U delta T by delta Z. So this is the overall Courant number, let's say we can take. Fine. So if we take the spacing along x-axis, along y-axis, along z-axis, so if we have turbulent, like if we have a boundary layer which is of 2D, let's say this is x and this is y. So here you can see we have this. Okay, so this is u, velocity is 0. This is u is equal to 0.99 times of u infinity. So this is happens to be a 2D. So when you take this z-axis, okay, so you have the one more bond layer which is developed in this direction. Okay, so you have this plane and you have in this plane other plane also. Fine. So what happens actually, we need to get what is x plus y plus z plus, okay, where we have delta s along x direction, delta s along y direction, delta s along z direction. So this is for 3D. So previously here we have seen for only along y direction actually. So when you want to uh, like when you want to see for a full 3D, so what we have here, so we have delta sx, delta sy, delta z. So here where again you have to calculate the value of like let's say the value of y plus and the value of tau wall along x y z axis and get the values of delta s, delta sy, delta z. Okay, this has impact of the core number, which in turn which have impact on stability. Fine. So with this we have seen the impact. So we have calculated the impact of the Reynolds number, skin friction coefficient, frictional velocity, and the spacing of grid points by varying Mach number. And additionally, we have shown the impact on the stability also. So we have seen that as the frictional, so we have seen that as the frictional velocity increases, the spacing decreases. So where frictional velocity is increased by frictional force of wall increasing and reference velocity increasing, Mach number increasing, Reynolds number increasing, and spacing decreases and skin friction coefficient decreases. So this vice versa will happen, and in turn the stability also, as the spacing is low, the stability actually still again the C value increases. So therefore the spacing and delta t should be actually taken care of. Fine. So in the next session we will see the other numerical problem for the other module. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.